Again, we're back. Today we're going to give you a little update on what we've been doing with our carbon-carbon flow capacitor. I'll start out with just a quick review of where we ended up last time. This is the typical cell that I've come up with. A couple 3D printed plates out of PLA, input port, output port for the anode, input port, output port for the cathode. The main problem with the first cell, which this is the performance was very poor. You'll see in a moment when I take it apart here that the blue paper towel separator material that I've been using sort of over-soaked, kind of collapsed in the middle of the cell. Don't think I got good coverage, etc. with the slurry on either side of it, so we proceeded to design something a little different. If you look inside here, which is now just a dried carbon mess, needs a little persuasion. Yeah, you can see the carbon cloth here with very little dried carbon on it. You see the pattern on what's left of the blue towel separator. It's not even completely soaked in. Having said that, the basic design is pretty good with the male and female plastic plates mating, sandwiching the separator in between, the carbon cloth contacts, nice little copper tabs on it. So anyway, we decided that we had to do something a little different. The main thing was to come up with a little bit better separator in there that wouldn't sag, soak up, kind of just collapse onto the current collectors, not allowing equal amounts of fluid on the anode and the cathode side. To do that, we did a couple things. We took our paper towel, and before we assembled it into the cell, we took, let's see, I think I've got a sample here, yeah. All we did was mix up a little cellulose acetate acetone, kind of starch this, if you will. Now it's a little bit stiffer, got a little bit of at least an initial waterproof coating on it as opposed to an uncoated piece. Use that for our separator. And I think the big thing that made a difference was on either side of the separator, we've got this little spacer. I don't know how well you can see this thing here, but we've got some threaded little plastic lines here holding these dots together. The dots are about a mil thick, and that spacer then, one on each side of the separator, keeps it from collapsing into the current collectors and allows a nice flow path through the cell. So although I've built up another cell, ran a test, we'll talk about that, and got some really good results. I think that's because now I'm using, the full active area that I have inside the cell. Just by way of review, there's nothing really fancy about the chemistry, the formula in the cell. We've got fish tank activated carbon. To that we add a little bit of carbon black. I'll put up a slide here with the exact ratios. This is Cabot's VXC-72 carbon black. Gives a nice little boost to the conductivity. That mixture goes in the ball mill for a few hours, turns it into, I would say something, close to a baking flour consistency. We mix that up with 5 molar KOH as our electrolyte. So the activated carbon, the carbon black, the electrolyte form a slurry. Throw in to help the mixing about 5 drops of glycerin to about 100 milliliters of the KOH. Stir that up, and actually you have to add the carbon fairly slowly. Keep stirring it. Takes over an hour to get a nice even slurry with the carbon suspended. Then we end up with our new cell, where I build the sandwich again with the spacers. Nothing real fancy here. You can see the valving to close off the outlet ports and open up the input ports, fill it on both the cathode and the anode side. And then for now, I guess it's not really fair to call this a flow capacitor, because what I'm doing is developing baseline performance in its static mode. In other words, when I fill it up, charge it, discharge it, without any flow through it, what's the best you can do? And then we'll talk a little bit about the next steps here as we actually do some flow experiments. But I'm pretty sure I got some pretty good coverage using the active area. This is a used plate from an earlier experiment, the carbon cloth on a tape backing, copper conductors on the end of it. This right here is the active area is 6.3 centimeters by 4.8 centimeters. That's approximately 30 square inches. When we take this cell and fill it up, charge and discharge it a few times just to make sure everything is stabilized and we're getting some consistent readings out of it. I was able to get with the 30 centimeter active area somewhere in the neighborhood of about 25 milliamp hours, which is about 4 times better than the similar cell without the spacers and the separator. One run actually was up there around 27 milliamp hours. I'm charging just barely above the limit for a water-based electrolyte. I'm charging to 1.4 volts. As we start to discharge it, it quickly drops down to about 1.2, 1.15 volts, and discharge down to about 0.4 volts. I have a little setup where I calculate both the time and the total capacity during those runs. And like I said, we hit 27 milliamp hours, which isn't too bad for 30 centimeters, and just a little over a 1 volt limit on the electrolyte. But that's kind of an aside note, since again what we're trying to develop here is a baseline recipe that then we can use consistently to try experiments in the flow mode rather than the static mode. The next steps are going to be thinking about design changes to the cell to make it a little bit easier to have reservoirs on the fill side, separate reservoirs on the output side. So we'll fill the cell up. We could do this either in 2 different ways, on a flow capacitor, or whether it's a flow battery. Either way, you can do it in a batch mode or a continuous mode. You can fill the cell up, output is closed off, charge whatever volume of slurried electrolyte you have in there, drain that out, store it, fill it up again, charge it, drain it out, store it, fill it up again, store it, and then go through the same process with taking the charged electrolyte slurry, if you will, and then using it to test the discharge characteristics of the cell. Fill the cell with the charged slurry, discharge it, empty it, fill it, discharge that, etc., etc. And you can do that as long as you continue to cycle it in that batch mode, each batch limited by the volume inside the cell. The other way, obviously, is to do it in a continuous mode, where you're continually, let's say like an IV drip, putting material into the cell, charging it up, and continually taking it out. What we'll do if we have to, if we get to the point of getting in that mode, is then obviously have a way to accurately, repeatably control the IV drip relative to, let's say, the charge current. You know, it might be so many milliliters per second per minute for so many milliamps of charge to make sure that the material inside the cell is, you know, not wasting any charge or, you know, sitting there being, quote, overcharged. But those are steps down the road. We'll see how that goes in either the continuous or the batch mode. I guess I'll kind of wrap it up here in a moment, just reminding everybody that the 5 molar KOH is pretty caustic. Your fingers do get a little slippery when you contact it. That is your skin dissolving. So if you go down that road with that electrolyte, be very, very cautious. We're going to be thinking about, maybe even have a little session here where we talk about some of the specific changes to how to mechanize, automate, you know, this flow process here. I'm pretty happy at this point with the viscosity that I've got. It looks like I've got a fairly good suspension. It looks like I've got enough conductivity in the slurry, at least to start these experiments. So we'll go from there. We'll include a slide here, again, as I think I maybe have done before with the recipe for the slurry and that sort of thing. But that's where we're at. Thanks for watching, and we hope to be back at you not too far down the road with finally a true flowing flow cell. That's all for now.